So we spent some time working on like what are the kinematics of this car jack as we're trying to figure out like how to design it, what thread count, like how many threads per inch as we're winding this thing up. The last thing we did was we figured out that if we want to move the car at a constant 3 millimeters per second, so we're turning the crank and the car is raising up slowly at 3 millimeters per second, then there's a certain angle, that the angle of our jack is changing at a certain rate, and at one point it's 0.0075 radians per second, like pretty slow. But then by time we get up to the top, we need to move this thing at an infinite number of radians per second. So question here is, one, is that possible? Like, is this something wrong with the way that we modeled things? Is this real? Like, what's going on? I wanted to kind of come back to this point where we figured out, the main thing was like, we know that if the top is moving at a constant rate, the rest of it is not moving at a constant rate. So I wanted to come back to that and figure out how to deal with this. What are initial thoughts on that? Can you rotate something at, let's not call it infinity, let's call it 6,000 radians per second? Can you do that? Yeah? Maybe? Theoretically? Okay. Theoretically? Yeah? Maybe? Why does it have to move so fast at the top? Like why does the angle need to like pivot so quickly as we're getting the jack like fully extended? Why is that happening? Is it a math error? Just like the number's actually 3, but we just did the math wrong and now it's infinity? Are we thinking or waiting for me to tell you something? I'm just trying to get a sense. Are you thinking about it? Not thinking about it? Not thinking.
Like, is it blocking when it gets to 0 degrees? Is there like some kind of like it's gonna get there like quicker, like it'll come to a halt and then we're going to stop and that's why.
Oh, like because, yeah, that is kind of like our maximum, right? Like, because if you go anywhere past that, at this point, like if we keep changing the angle, they would like fold in on themselves and the thing would fall back down, kind of like that. That's true. Yeah, so there is something weird about like at the top, there's something different. It's like an inflection point. But if the angle keeps going that way, so if you think about it, this is really what we did was we said that we were creating constraint that the velocity of the top was a constant. So it's as if like, have you ever taken opened up a folding chair? Something like that? Like you just grab the two ends and you're not carefully opening it. You're just ripping it open and hoping that everything falls into place. That's kind of what we're doing here with our constraint. Like, no matter what, car jack is going to open at this, well, open this way at a constant rate. Everything else, do whatever you need to. Like, we don't care. And it's fine to say that, but in reality, it's going to lead to some weird results where some things are moving a lot faster than we thought they would. Not the whole time, but sometimes. Something to add?
Man, I was just thinking, like, whenever I've seen some kind of, like, example of this in, like, my experience, it's just, like, at the start, it, like, starts, like, the angle is decreasing at some rate, but it, like, increases faster and faster. So at
Yeah.
the very end, I can visualize it increasing at, like, a very high rate compared to the initial. But, like, I don't think infinity is, like, a rational answer.
Yeah. Yeah, and infinity is really, like it's not actually going to be infinity, right? Like, because part of it is that we're not raising the car at that speed, but it is something, if we were saying that the car is moving at that speed and everything else was moving with it, then there would be like a snap through event where the thing is moving super fast and then it folds back in on itself and collapses. We have a screw to keep things in place, so there's like a stabilizing element to it. But as you think about these systems, it is real. Like you can have real, like very quick changes like that. They're not infinite, but they're big. In reality, it slows everything else down to match up those constraints. So the question is, are we happy with this constraint that we want the car to move at a certain rate, or do we want to go back and revise that and say, like, maybe the pin should be moving at a certain rate? Do you know what I mean by that? Like, since we're going to be turning the crank, rather than saying the crank has to change how fast it's moving to make the car move at a certain rate, we could say, crank's going to move this rate, the car is going to do anything it needs to keep up with us cranking it. What do you want to do? Sign, seal, deliver, or revise? This is your chance. You get to do an engineering decision. Revise our constraints, because we put a constraint that car has to move, but we could change that constraint and say that collar has to move. Do we want to say collar is moving, or do we want to leave it as car? Yeah.
I feel like since the collar is like the most strangest, like it's not straightforward movement. So I think if we constrain that, then it'll be like easier to deal with the path movement. And
You think it'll be easier if we go back and look at like collar motion rather than like
or we
car
can just
motion?
try it and then just
We can try, yeah.
because I feel like since it moves in like an arc, and it'll just make life easier if we like say it's like a constant thing.
Yep. Yeah, we could do that. What do we think about that?
Yeah,
Try it?
it's more realistic, but
Okay.
to move constant than
Yeah, if you're turning the screw, like you're gonna keep decreasing like that the X position,
Yeah.
right? Like that distance keeps getting smaller. Try it. All right. So if we want the car to move 3 millimeters per second, I'm looking at my equations. Before we said car is going to move at a constant 3 millimeters per second. Here, if I want this number to be 3, then this number has got to be like double that, because this one's 2 times L theta dot, this one's 1 times L theta dot. So I could say 6 millimeters per second is my thread speed. Like that's how fast my thread is moving along. Seem reasonable? All right. So then we have this question. So if the thread's moving 6 millimeters per second, how fast is car moving? How fast is the jack moving up? What do we think? We can give it a shot. See what we can come up with. You can even ask questions if you're not sure where to start. So, like, A is sort of like where that collar is on the red. So A is moving in a circle, and then B is where the car is attached. So this is moving in a circle, and this moving straight up.
Okay, so it's not linear.
I think it's not linear. Yeah. Roughly, you can kind of see A is moving 1 meter. B is kind of it's not always that case. That's not so roughly, some people kind of forget that angles.
RB is the vertical distance, or A is the distance. And the velocity.
Do you know like this? What you're trying to do with
This.
Oh, I know something like a jack. I'm guessing full.
so far we So we had some time to think about it. Did anyone come up with like a number or an equation for VB? If not, what questions did you come up with? Questions are just as good as answers. How do I fill in this? This question mark. VA is 6. What is VB? Yeah. VA, so on Wednesday we were talking about, so quick answer is VA is a chosen number. That, you know, it's not that like that is the number that has to be for a jack. So we did that based on if you're lifting a jack and it takes 2 minutes, like assume that someone can move it in 2 minutes. We took total distance divided by 2 minutes and figured out 3 millimeters per second was our number. Yeah. Thanks for clarifying. Yeah. No. Yeah, I appreciate it. And then I doubled it because if this distance has to be whatever, X, then we need to move this one 2X, or at least like we want the speed to be 2X. Cool. what do we even do to get there? Like, what is there a connection between collar motion and upward motion? Let's just do we think if I move collar, car moves up? Okay, so there's got to be some connection because it's still 1 degree of freedom system. We're changing how we're actuating it. We're not saying we're pulling on the car, we're pushing on that pivot joint. There's got to be some kind of connection. Cool. What about our constraint equations? Which one is the x component of VA? What's describing that collar motion?
The L theta dot something.
Yeah. This is VAX. We're saying that this value has to be 6 millimeters per second. Yeah.
Sorry, I guess when you got that, how did you get those equations?
Those equations?
Yeah.
Those were given to me. I went to the top of a mountain and Moses was there with a burning bush. And he's like, from now on, you will use these equations for these car jack systems. And I said, yes, thank you. And I brought them back down the mountain. I'm being facetious, hopefully. It's Purim, like, soon, so it's time to be fun. All right, let's back up then. How do we get there? The way I usually do like constraint equations is figure out what are the variables that describe this thing. So to me, main thing is like if I know angle, then I know everything about the car jack. And then I have a mirror image of it over here. So if I know this one angle, I'm good to go. So then I want to figure out where is A, where is B, in terms of like what is this vector, RA? Really? I don't really need that, RBA, but, and then what is this vector, RB? Those were the two things that I was trying to figure out. And I figured out, I say it was a team effort. We did it together. We were here. We figured out RA is L sine theta plus L cosine theta. And then RB is 2 times L cosine theta. So like double that, put it up top. And that's where, and then RB is always kind of 0 x position, just moving straight up and down. And then based on that, if I know constraints on position, I know constraints on velocity, because velocity is a change in position. So if it's constrained, it's still a derivative of that constraint. And these two equations, VA and VB, are derivatives of RA and RB. That's where like those are coming from. And it's good to kind of walk through that. Even if you remember doing this, sometimes it's nice to like walk through why we did these steps rather than just like furiously writing down the math. And then also it helps because now I know that x component is my constraint. Question? Thinking?
I was thinking, can we find theta? Like set them equal, find theta, and then plug it into the RA equation? Or something like that. Or we can find VB.
Yeah.
Because it's derivative, so can
Yeah. So
integrate
this is like exactly true. Like this number that we said, 6 millimeter, that is L theta dot cosine theta. And VB, this is 2 L theta dot sine theta. So it's like we have two equations and one unknown, right? I guess two equations, two unknowns, because we don't know theta dot and we don't know VB. So we can solve for both of those since we have two equations. How does that sound? You want to try that? All right, let's give that a shot and see where we come up with. What we come up with.
What was the data dot?
That one is so like that. If you think about like A moving around in a circle, theta dot is like how fast it's rotating. Technically, it's also the other one. Rotation is going to go too, but here, mostly just been talking about that bottom angle.
So all this stuff that is less than say one theta is not one theta. Are we
It's all gotta be connected, right?
Yeah.
Because if you're moving one thing, the other thing has to move. The only difference is,
okay,
so we'll end up with similar problems at 0 and 90 because those are kind of extremes.
sort of just taking a step back, what you're saying from a different way.
Yeah.
Yeah.
Yeah, that's okay. Oh, good luck. Yeah. Yeah. It should be easy, but it ends up being so complicated. Yeah. 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 It's just there's been a few setbacks. There's no fun. Yeah. Sometimes I leave it because some people end up like 2 finals on Monday and this is like the third. And then they can reset. It's like 3. Sometimes I leave it. No one sees the search report. So now the idea is just remember these call them.
Yeah. This is just like drawing stuff. Just using the same
All right, you ready for some fancy math? It's not that fancy, but why do that? Why would I do that? Now we got a ratio, right? Do we have, does it depend on how long these bars are? 10 versus 10 centimeters, 10 meters? No, those cancel out. What about the theta dots? No, not really. Those cancel out. Yeah, I think we're all set, right? 12 millimeters per second times tan theta. What's with that tan theta? Why is that? Why do we have a tangent there? Is that okay? It's like that. Yeah, something that has to do with like the fact that it's moving in a circle, right? That we're driving this thing upwards, but we're using a circle to do it. And that's okay. All right, so when is this thing going to be 12 millimeters per second? Like when is it moving at 12 millimeters per second? When is tan theta 1? 45, yeah, so halfway. That'll be like how fast it's moving when we're halfway there. What about when we're at 90 degrees? What's tan of 90? 0, okay. A little weird. It's not going to be moving at all when it's at 0? When it's at 90?
You do it undefined though, because it's 1 over 0.
Tan, is it 0 or 1 over 0? 1 over 0. All right. There's 0 in there. All right. That's a tough part with crowd work. You never know what the crowd is going to give you. All right, so undefined. Somewhere this way. Like, that's our asymptote for tan. Okay, cool. And then what about 0? That's our other kind of extreme. 0? Weird. Right, so we'll have some kind of curve like this, or maybe on average it is 6 millimeters per second, something. What is it?
Wouldn't it be like going down, like after it passes 45?
Does it go? I think tan theta go up. Which one? Zigzag? Sine 0 over cosine is 0.
Oh no, you're right. Yeah, no, it increases.
It's right? Okay, all right. I think it makes sense to me, but I'm not. So it's a little weird, but we're not talking about things that the human doesn't have to make it move 20 or whatever, 20 meters per second. It's just the system will respond that way. Like we're just gonna move the screw at a constant rate, and we don't have to worry about everything else moving quickly. And we have a screw, we have something like keeping it in position, so it's not too big of a deal. It's a little, the beginning's a little weird, like when it is flat, you're gonna drive the screw in, but really, it's gotta like pop up. Most of the motion is upwards rather than inwards. But that's okay. We'll get there. All right, that was fun. But now, nice part is we've got this relation of like, and we could even make it more general. We chose a number for VA, but really we could say VB is 2 VAX tan theta. So even if we go back and change, like, all right, I don't want to move it at 3, I want to move it at 10 millimeters per second, we have a general kind of relation between those. Because we did all the math work ahead of time to get to that point. I'm gonna scroll up and then come back down because the next thing is trying to figure out our kinetic description for how much load the screw is holding. So we're turning that crank, and the screw is trying to hold the whole weight of the, not the whole weight of the car, but a quarter of the car. We said maybe a third of the weight of the car on Wednesday or Friday. So now what I want to do is figure out what is the load in that screw. It's probably going to change. Like we already saw that motion depends on the configuration as the thing's moving. But that's the next step. Is like, what is the load in that screw whenever we have that load of the car? And we'll put times 9.81, so we have newtons instead of, so that I know that this is my applied load, and then let's do this. I know this is my applied load. The tension in the screw is the load that I want to figure out, like how much force that screw needs to hold. What other forces do we need to look at? How do I finish off? What am I starting to draw here? The free body diagram? Yeah. Yeah, so free body diagram. What's missing? Any other forces on there? Yeah, there's gotta be something keeping it from going down, right? Right now everything's inward and down, right? Something, right? Yeah, I agree.
You have the normal force of the ground pushing like that.
Yeah, ground has gotta be there somehow. Yep. Oh, for the car. Really? Kind of the assumption is that picking up a quarter of the car. Like just, yeah, I mean, I guess like if you factor in the fact that the car is tilting, but it would be like times cosine of the angle of the car. And cosine of the angle is really, really close to 1. So it would be 99.9% of that initial quarter. Yeah. Yeah. Yeah, definitely. I like that. Mm-hmm. Yeah, you want to split it at each hinge.
So I kind of envision a triangle here,
Yep.
so that we can split it up.
Yeah. I mean, basically, we kind of built the whole bunch of little triangles, right? Like little trusses. Yeah, that would make sense to me. All right, this was a good review on free body diagrams of structures. And it's not easy. There's hard part here is recognizing what is an internal force and what is an external force. So internal forces, they're there, like they absolutely exist, but they're not part of your free body diagram. Because the free body diagram is just showing like what are the external things to this one thing. So in terms of like the universe as a whole, the free body diagram is just a dot. There's just nothing happening. No forces, no external forces outwards, other than like, I don't know, God's finger to like get the universe started, the initial impulse or something, depending on your view of the universe, or the spaghetti monster. I don't know, whoever you think started the whole bang. So like on these corners, on these side corners, we have the tension screw drawn. I drew it as an external force because really I'm considering like if I remove that screw, what is the force necessary to keep this thing in the shape that the screw was holding it in. So that screw force is an internal force. I just took it out of my free body diagram and drew it in there anyway. That was like those cuts, like in the statics from beam dynamics. Make a cut, make a little squiggly line, then you have a moment, you have a shear force, all coming back. It is all connected, all this engineering stuff. I know sometimes it feels disconnected of like, memorize the equation, plug in the numbers, get the A, move on, forget everything. But it is all, it's part of your work. So then next, people noticed there's got to be some normal forces, right? Something like this. Here's another tip. If there's a hinge, there's always two components of force. Sometimes one of them is 0, but there's gotta be 2. Because the hinge does not let it move X or Y, and it doesn't let it move in the X, and it doesn't let it move in the Y. And that's why we started off with like kinematic descriptions, because we were figuring out where's everything fixed. So if I have a hinge here and here, there's got to be, there's some symmetry, so I'm gonna make a quick assumption. There's gotta be some Rx this way, some Rx that way, right? This one, I didn't see this one, that's why I was kind of like explaining why I'm putting it on there. Other forces? Maybe?
What is the RX of the
Rx would be the, so like if tension of the screw is pointing this way, really this whole thing should move that way. But there's gotta be something preventing that. I guess really I drew it opposite direction. But here it's gotta be 0 is the main, the sum of the forces has to be 0 there. Yeah.
Would there be the normal force of the car at the top plate?
So, like, is there something this way from like,
Yeah, that's equal to the force that I push you over there.
like, and, oh, okay, it's catching up. I think it's, yeah, there we go,
Yeah.
like that.
And then instead of the 2 wings down there, I mean, for me, I would write RY. That makes
RY, yeah. Well, yeah, I was just saying, like, some people are pointing out, like, it's touching the ground. So normal, or you could call it RY. But this normal from the car, this one is, it wouldn't be included in here because the car is not part of my free body diagram. It's sort of like removing and saying, like, what is the force that the car creates by being in contact with my jack system? Again, a lot of this academic stuff can be kind of pedantic, of like what's external versus internal. Technically, everything's an internal force if your free body diagram incorporates enough stuff, but we want to make it small enough that it's simple and kind of helpful. So we can't include both, because if you include both the normal up and the force down, total force is 0. Now there is no. Now we're just moving a jack, just for fun. It is pretty fun, like a fidget spinner, I guess. Just a 30-pound fidget spinner. I guess they're not that heavy, maybe like 10 pounds. How are we doing? Almost, are we out of time? What time? Yeah, we're out of time. All right. You can be more upfront. You can be like, dude, cut it. Paid for 50 minutes, not 52. All right, see you Wednesday.